students, welcome to class 10. Hope you have studied the previous videos from previous 9th, 8th video. Okay, very important. So connectivity should be there, otherwise you will not understand the concepts. Okay, so now in the last video we had learned regarding the synthesis of arenes. Okay, so this we are learning. So we will go for one more type of synthesis of the arenes, that is well called as Friedel-Crafts reaction. Okay, Friedel-Crafts reaction. Okay, where we can see that chromium chloride CrCl3 is been treated with aluminium in the presence of catalyst AlCl3, and if you take 6 of C6H6 moles of benzene here, so you are going to get this compound neta 6C6H6 twice. Okay, cationic species you are going to get this on reduction, so you are going to get this compound Cr neta 6C6H twice, like this. Okay, so this is what we are going to get here, Friedel-Crafts reaction. So this aluminium, so it is used for the reduction of reducing the metal. Okay, reduction of the metal. Okay, so it's a type of Friedel-Crafts reaction. So when we treat it with AlCl3, it's acting as a catalyst as well as reduction of the metal here, chromium plus 3 state here. So what will happen here, first you get this cationic species here. Okay, and this on reduction, so you are going to get this species. Okay, so this is the one type of synthesis of the arene complexes. Okay, so another type you can go for synthesis, you can mention from dienes. Okay, from dienes, how it is been prepared, you take 1,3-cyclohexadiene, 1,3-cyclohexadiene. Okay, when you treat this with ruthenium chloride, RuCl3, okay, cyclohexadiene treated with ruthenium chloride, you are going to get this compound. Okay, again you are going to get in compound, that is C6H6. okay, ruthenium. Okay, so ruthenium chloride is you are going to get here like this. Okay, with one of the bridging chloride, like this twice. Okay, this is what you are going to get this. Okay, neta 6C6H ruthenium chloride, you are treating with ruthenium chloride RuCl3 with this 1,3-cyclohexadiene. Okay, 1,3-cyclohexadiene, so like this. See here, so this thing also, this is a mu Cl, bridged chloride also is going to form twice. So this is also one type of arene complexes obtained from the dienes. Okay, so arenes bind only to, actually if you see this, so they are going to bind only with to the low valent, okay, metals, low valent metals. This you have to keep in the mind, so that the metal salt of the higher oxidation state are reduced here. Okay, in the presence of the ligand. So that is important here. So, okay, so that's why the arenes are binding only to the low valent metals. Okay, so the metal salts which are we are taken here, like AlCl3 or some other metal salts, any salts what we are taking here, metal salts, so of higher oxidation state what we are taking here, are reduced in the presence of the ligand. So like this. So this is what about the preparation of the arene complexes, some of the arene complexes. Okay, now if you see the molecular orbital picture, okay, molecular orbital picture of this arenes, they are similar to cyclopentadiene. We'll go to the molecular orbital the last moment. Okay, so they are similar to this cyclopentadienyl complexes, but these arene ligands are weaker. So what happens if you consider the cyclopentadiene, these arene ligands are weaker. Okay, this you have to keep in the mind. So they are a weaker donor to metals, so they are weak donor atom to the metals. Okay, so they don't donate as such to the metals here. So one thing you have to keep, and the binding depletes electron densities. Upon binding, what happens, it deplete, okay, the electron density, it depletes the electron density on the ring. So it depletes the electron obviously on the ring, and that's why what will happen here, now it becomes very subject to the nucleophilic attack. Okay, now that ring becomes subject to a nucleophilic attacks. Okay, not electrophile but nucleophilic attack, because the electron will be given, you know, so depletes, the electron depletion from the ring takes place upon binding here. So this is what you have to keep in the mind. Now in 1954, dibenzene chromium, this was the first year, 1954 dibenzene chromium. Okay, so dibenzene chromium was characterized via Grignard's reagent. This also sometimes they will ask. So dibenzene chromium was characterized using Grignard's reagent. That is what he has taken, this phenyl magnesium bromide, and this was treated with chromium chloride salt, Cr metal salt here, in the presence of diethyl ethers. Okay, C2O diethyl ether. So to give this compound, chromium phenyl is there, H3 Et2O thrice something, this compound. This is a monohapto type of compound. This rearranges to give this compound. Okay, neta 6 C6H6 twice cationic species. Okay, plus now what happens, this on reduction with Na2S2O4, that is your sodium thionide, sodium dithionide, Na2S2O4. So you are going to get the this compound, that is your Cr neta 6 C6H6 twice, that is your dibenzene chromium, like this. Okay, so this is sometimes dibenzene chromium 1954 characterized Grignard's reagent, first prepared by phenyl magnesium bromide in the presence of metal salt CrCl3 and diethyl ether. You are going to get this species here, which is a monohapto here. Okay, a type of species here, and from this what will happen, your rearrangement takes place and you are going to get this cat ionic form. Okay, ionic form, and this on reduction with the sodium dithionide, so you are going to get this dibenzene chromium complex. Okay, and this is a neutral metallocene. Okay, so you are going to get this neutral metallocene here, and if you see this benzene complex is of this such type of like chromium, molybdenum and tungsten. Okay, they are very air sensitive, Okay, so if you consider the complexes of the benzene of this type of chromium, molybdenum or tungsten, they are very air sensitive. Okay, and this chromium, dibenzene chromium, what we have synthesized here, it is black solid. Okay, it is a black solid. Okay, this dibenzene chromium is a black solid having with the melting point around 280 degree centigrade, 280 degree centigrade. Okay, so this is what about the small part of this arene complexes. And sometimes we can prepare these arene complexes by taking this solid form of the metal, then vaporizing it, okay, in vacuum to the gaseous form, in the presence of vacuum in the gaseous form, and just treating this with your benzene vapors here, C6H6. So you are going to get this type of H6 twice metal dibenzene. Very simple. Okay, solid form of metal vaporized in the presence of vacuum. Okay, and then treated with this benzene, and you are going to get the arene complexes. Okay, so this is how also it can be prepared. Benzene arene complexes can be prepared. Now going to the next concept, the rings of the dibenzene. Okay, so if you take the rings now of the dibenzene, for example chromium, molybdenum, tungsten, okay, they are eclipsed, form. Okay, and they have a small rotational barrier, and they have very small rotational barrier. They have very small rotational barrier. So if you see ferrocene, it is not so very hard here, but unlike ferrocene, if you see this benzene arene complex of these, they are having very small rotational barrier. So what happens with this type of property, that they are labile, they have the labile rings, now. Okay, labile means the rings can be shifted and can be displaced. For example, if you take this CrCO6, okay, hexacarbonyl chromium, and if you treat this with you take this like this chromium, like this. Okay, so what will happens now, as I said, these are having the small rotational barrier, and that's why the rings are labile. What will happen, they can be displaced in this way, so we can get it into form like this, CrCO, like this here. So like this, they are going to displaced. One of the benzene ring can be displaced, and we get in this way. Two molecules of this we are going to get here. Okay, so the benzene ring can be removed sometimes. In some cases, you can see that this benzene ring can be removed also. So this benzene can be removed by treating with the very competitive ligands, very strong ligands. Okay, if you take very strong ligands, okay, and treat this benzene ring can also be removed. Such type of flexibility we can see in this arene complexes. For example, if you take this chromium nita 6, okay, dimethylene chromium, and you treat with PF3, okay, trifluorophosphine. So what will happen, so this is going to replace now, so you are going to get PF3 6 times, okay. So chromium, so this will be reflected, now benzene can be replaced here, and PF3 trifluorophosphor, phosphine, which is very strong ligand compared to this benzene, it is going to replace here, and you are going to get here C6 H6 out, like this. So such type of this can also be happened in the arene complexes, where there is removed completely from the ligand. Arenes are removed completely from the reactions, okay. Now if you see some of the heteroatoms also, I will write here some of the heteroatom 6 electron donor. See, they are analogous to benzene, analogous to benzene, okay. So some heteroatoms 6 electron donor which is analogous to benzene, okay. So they are also going to be act like this this type of reactions here. So like for example, you can take it of phosphazine, okay, like this, okay. So Cr, you can take this CO, okay. This is called as phosphobenzene, okay. So phosphorus is here, phosphobenzene, or borabenzene, sometimes heteroatoms, borabenzene. So borabenzene means what? Same thing here, boron, you can write it here like this, okay. And you can give some iron in this way, okay, boron, like this, okay, substituted with some of the, like this. So this is your borabenzene, okay, heteroatom which is analogous to benzene, and they are also acting as a 6 electron donor, okay, and they are going to form some complexes. Then your borazine, what is that borazine? So nitrogen boron compound, boron, is it right? Then nitrogen boron, so this is, I think this is a compound here, again chromium, you can go for like this, okay, like this. So this is your borazine. So this also is acting as a heteroatom which is analogous to benzene. And then arsabenzene is there, so you can take, arsa means arsenic, okay. So like this, so you take one compound of chromium, again you can take it like this, like this. This is called arsabenzene, okay, arsabenzene. So this type of these are the compounds which are analogous to benzene, and they are also acting as these arene complexes, and they are also 6 electron donors, and they are going to form the nita 6 type of complexes on treating with the metals, okay. So this also you have to keep in the mind, like phosphobenzene, borabenzene, then borazine, arsabenzene. So some like this you have to keep in the mind, so it will help you, okay. Now similar to this nita 6, okay, so there is some of the compounds like cycloheptatrine, cycloheptatrine, okay. There are some of the compounds like nita 6, there are 7, cyclohepta means 7, okay. And tropylium complexes, okay, tropylium complexes, cycloheptatrine or tropylium complexes. So they are also acting as a 6 electron, though it is hepta here, so but these also are acting as 6 electron donor complexes, 6 electron donor complexes similar to those of benzene, okay. As benzene is going to form, similarly these complexes are also 6 electron donor similar to benzene, but it differs in the delocalization, but it differs in, because hepta is there, so that's why it is differ in delocalization of it differs in delocalization of pi electrons, okay. So like, because it's having C7He8, okay, so C7He8 cyclohepta trine. So it is just like this, 1 2 3 4 5 6 7. So this is what we can represent here, 1, then we can present it here, 1 left, 2 3, like this, okay. And this is what molybdenum, these all things is joined like this, okay, and you get here molybdenum, you can state here with having C triple bond O, triple bond O. Okay, molybdenum complex is, so it is tricarbonyl. The name of this is tricarbonyl. This is tricarbonyl 1 2 3. So tricarbonyl cycloheptatriene. This is cyclohepta 7 carbon cycloheptatriene. Triene means 3 1 2 3 bond, molybdenum 0. Okay, complex. So here, and if you see the bond length also in picometer, okay, bond length if you see the picometer, so this is 151 picometer, 134 picometer, 146 picometer, 138 picometer, and this bond here which is going to attach with the molybdenum, it is also around 140 picometer, like this. Okay, so bond length also varies here in all this this one. That's why it differs in the delocalization of the electrons compared to the benzene. So this is what you have to keep in the mind. And what happens, this cycloheptatriene complex is yes, here I will write here. So what happens now here, this cycloheptatriene complexes, what we had given here, they can be now oxidized. Okay, cycloheptatriene complexes can be oxidized. Okay, they can be oxidized. So this is can be oxidized. That is oxidized means proton ion abstract. Okay, we can abstract the proton from that to form cycloheptatrienyl, to form the cycloheptatrienyl tropylium cation, cycloheptatrienyl cation. That is called tropylium cation, we call it, no? So similarly, so that can be done in this way: 1 2 3 4 5 6 7, 1 2 3 here. Okay, so this is joined with the molybdenum, carbonyl. When you treat this with the triphenyl carbon complex here, carbon plus, okay, and BF4 minus. This is the condition here. So you are going to get now this whatever the cyclohepta tricarbonyl molybdenum 0 complex is there. So this is going to be converted to cycloheptatriene. There is tropylium cation in the presence of this, okay, intermediate. So now what you are going to get here is somewhat 1 2 3 4 5 6 7. So you do it properly, so like this. Okay, and you are going to get here molybdenum CO like this, and here plus. So this is your tropylium, we call it as a tropylium cation. Remember this. Okay, this is called your tropylium cation, followed by here BF4 minus. Okay, BF4 minus plus. So this is abstraction of the proton. Okay, so that's why it is forming the cation as PH3CH. So plus PH3CH you are going to get here. Okay, now this tropylium, what is this main important of this is this tropylium ring is a planar. Okay, so this tropylium ring is a planar. Okay, this is a planar ring, and it's having the equal carbon-carbon distance is almost equal. Okay, equal carbon-carbon distance like we see in the benzene. Okay, so benzene, how the equal this will be there, same thing in this cation we are going to find equal distance here. And this anion, whatever the cyclopentadiene anion, like this, they are also, this tropylium cation is also aromatic in nature. So they are also aromatic in nature. This tropylium cation are also aromatic in nature, and it is a 6 electron species. Okay, it is a 6 electron species like cyclopentadiene anion. Okay, like cyclopentadiene anion. So how they are aromatic in nature, similarly this tropylium is also aromatic in nature and 6 electron species. Okay, so this is what about this tropylium anion. Okay, so this is what about I think more than sufficient for today's video. Okay. Okay, in the next video we will learn regarding cyclooctatetraene. Okay, that is carbonate. Okay, cyclooctatetraene. So this we will learn. Okay, and whatever some part is left, that we will complete in the next video. If I get some molecular orbit diagram of benzene also, okay, so that also we will learn. Simple, as you have done already for cyclopentadiene, that's what I have told you. So this also we have to we can do in simple way. Okay, so like this, down, down, down. Right. So we'll see that. Okay, so this is how MOT diagram we can make, and we can study for this different psi 1, psi 2, psi 3, psi 4, psi 5, psi 6. Okay, so it is going to give 6 molecular orbitals. Okay, so we'll learn this in the last concept of this. After this cycloheptatriene, so we'll go for cyclooctatetraene finishing part, and then the last we will go for this simple structure and bonding parameter of this. Okay, so hope you understood this video. Okay, so in next this one video we'll learn regarding the other concept of this. Okay, so what you do, you learn you make this notes properly, because each day and every day I'm sending you the videos. Okay, so now see, at the most within a week we have sent the videos from 1 to 10 now. Okay, and I'm seeing that very less views is coming from each videos, because I come to know that from my channel. So that should not be should be, that is not a good. Okay, so 59 students strength is there, 57, 58. So but views are very less for each videos. That is a very bad sign. So each day all students should go through this. What time at the most you get? Half an hour for this you can spend, and you can make points of this and make a notes. Okay, so do that, then only you will enjoy this class and understand the class, because a lot of things are there behind this, not only this concept, this simple I'm going, but lot of things are there behind this, and that you are going to face whenever we are solving these NET questions. Okay, after this completion, so that we will do it. So that's why don't take very easy. uh, Frequently go on to these videos. Okay, not make the points nicely, write down, and in Zoom meeting and all, when we are face to face, then you can ask some points questions and get into the concepts clarity in your mind. Okay, thank you very much.